Good morning, everyone. Good morning, everyone. Yeah. So, hope people are there. Yes. Okay. Now, yesterday we have been discussed about up to the determination of the means first method, and that method. Yes. So that method is known as means method of dimension analysis, that is known as Redis method and Buckingham's pi theorem. But you know that we are going to use the Buckingham's pi theorem only, not the Redis method. Now let's see the next, the last and major application of dimensional analysis is model studies. Model studies. So the model studies is the what is the purpose of the model studies? The purpose of the model studies is to replicate the results, from the experimental setup to the practical conditions. So in order to design a structure or any system, we are going to do that experiments in the laboratory first, and then we, based upon the results from the experiments, then we design and we construct the actual structure in the field. So for this first model, so model is a replica of our first. Let me write it as a prototype. 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 Prototype means actual structure or system. Actual structure or system. That's going to be the prototype. And what about the model? Model means a replica of prototype which may be smaller or larger or same size of prototype. Same size of the prototype. See, generally in our civil engineering, we take the prototypes as a large scales, and the models are going to be the small scales. So in micro engineering also, if you want to study the micro levels, then you are going to make it as a large size. Okay, so based upon the type of engineering we are going to see, and based upon the type of discussion or type of system we are going to analyze, so the model size is going to be either same as the prototype, or small of the prototype, or large of the prototype. Okay. So it can be smaller or larger, or even same size, and that depending upon the fluid flow or fluid problems. But now in our civil engineering, mostly what we deal is nothing but the prototypes are going to be larger one and models are going to be the small one. Okay. So now, how to conduct the model studies. Now, in order to conduct the model studies, the model and prototype should be similar to each other. To conduct model studies, to conduct model studies. Model and prototype should be completely similar to each other. They should be completely similar to each other. Okay. So now, so what is the meaning of this similarity, sir? What is the meaning of this similarity? So for this, let's take prototype, and model. So let us take the rectangular channel. So because as we have been discussed about the channel flow, so now let's say it as a open channel flow. Okay. So in the case of the open channels, now let's take the prototype is going to be a rectangular channel, and whatever this is nothing but the depth of flow. So this is the actual rectangular channel. So I want to design, I'll ask you, I want to design as a hydraulically efficient section. A rectangle is a hydraulically efficient section. You know the meaning of the hydraulically efficient section? Maximum discharge. Yes or no? So for that, what is the condition I mentioned is Q means B is equal to 2I for the rectangle. Now how much discharge? What is the magnitude of the discharge that I have to send? That we are going to discuss in the laboratory first, and how those are flows, whether it is a steady flow or unsteady flow, whether hydrogen occurs or not in those, everything we are going to analyze now. This is our prototype. Let's take the width of the prototype as BP, and similarly the model, you see here, this is the model. So I am taking in the laboratory a small scale model. In our civil engineering, mostly we deal with the small scale models only. Okay. So now here the depth of flow is of prototype is YP, and depth of model is YM, and width of model is going to be DM. Okay. So first of all, while you are going to design that, there are two different type of the models. What are those? Types of models are: number one, undistorted models. What is the meaning of the name undistorted? Undistorted means no distortion at all. Undistorted means no distortion at all. So the meaning of the undistorted models is the no distortion at all, which means the model and the prototype should be geometrically similar to each other. The model and the prototype shapes should be geometrically, means the shapes of the model and the prototype should be similar to each other. So shape of model should be similar to prototype. So when the shape of the model is going to be similar to prototype, then we call it as an undistorted model. We can say it as a geometrically similar. What is the meaning of geometrically similar? The meaning of the geometrical similar is going to be a shape of the model should be similar to the prototype. Sir, how come the shape of the model is going to be similar to prototype, sir? That is going to be happen if the ratios of the dimensions in the model to the prototype. The ratio of the dimensions in the model to the prototype, if everything is going to be same, then we are going to call it as a undistorted model. So what is this? First of all, you see there are horizontal dimensions, are there or not? What are the horizontal dimensions? Width. So now from this horizontal, so horizontal scale ratio represented with LH. So horizontal scale ratio. So what is the meaning of the horizontal scale ratio? LH is nothing but whatever the width of the model to the prototype or length of model to the prototype. This is a horizontal scale ratio. Okay. Now vertical scale ratio. Vertical scale ratio, LV. So the meaning of LV is whatever the vertical scale ratio means. That see the ratio. If I mention a ratio, that is nothing but model to prototype, my dear. That is nothing but the model to the prototype. Okay. So now, if I mention the ratio, that's going to be the model to prototype. That's going to be model to prototype. Okay. Now I am mentioning you the vertical scale ratio. Vertical scale ratio means what are the vertical dimensions over here? Whatever the depth in the model to depth to the prototype, height in the model to height to the prototype. Those are so vertical scale dimensions. Now, when do you say the undistorted models? The shape of a model should be similar to prototype, and that is going to be happen if the ratios means the meaning of geometrical similar is if the ratio of dimensions in both the horizontal and the vertical direction are same. So now when do we call this one is when LH is equals to LV is equals to LR. In simple words, if the ratio of the dimensions in the model to the prototype in all the directions are same, then they are geometrically similar, then we are going to call it as undistorted models. Then we are going to call it as undistorted models. And second one, distorted models. So in the case of the distorted models, LH is not equals to LV. The ratio, the scale ratio in the vertical direction is different and the horizontal direction is going to be different. So when the scale ratio is different, then the shapes are not going to be similar to each other. Then the shapes are not going to be similar to each other. So the angle should also be in scale ratio. Yes, whatever the dimensions that represents, right, that everything should be in the scale ratio. Okay. So generally the distorted models are nothing but the reverse. In the case of the reverse natural channels, in the case of the natural channels, in the case of the natural channels, you know that. So for the natural channels, the shape is going to be irregular. Yes, for the natural channels, the shape is going to be the irregular. So when the shape is going to be irregular, my dear, for the shape is going to be irregular, my dear, where you are going to discuss about that. In the case of the river, the shape is irregular. When the shape is irregular, can you made a model which is going to be irregular shape? No. So for the analysis of the rivers, the prototype structure shape is different and the model is going to be different, which means their scale ratios are going to be different. So then they are not going to be geometrically similar. Okay. So these are the different type of the models, but mostly we discuss about the undistorted models only. Now, as I said you, in order to conduct the model studies, they are going to be completely similar to each other, and they should be completely similar to each other. Now let's see what are the type of similarities. Types of similarities. Types of similarity. So number one, geometric similarity. What is the meaning of geometric similarity? Just now I said you the meaning of geometric similarity are shapes should be similar to each other. Shapes should be similar. So what is the meaning of this one, sir? The meaning of this one is the ratio of dimensions in model to prototype in any direction should remain constant. Should remain constant. Okay. So what is the meaning of this? The ratio of the dimensions in the model to the prototype in any direction. So let's take the width of the model to the width of prototype. Okay, that's a ratio of dimension model to the prototype. Width to the prototype means model to the prototype, and in any direction means length to the model to the length to the prototype, depth to the model to the prototype, and height of model to the height of prototype. So you take any direction, the ratio of those dimensions should constant. Whatever this ratio, which is nothing but LV is equals to LH is equals to LR, and LR is known as a scale ratio. LR is known as a scale ratio. So first one is going to be the geometric similarity. So whatever the L represents the vertical scale ratio, LH represents the horizontal scale ratio, and LR means it's a scale ratio. Next, similarly, second one, kinematic similarity. See, I told you for a fluid problems, there are three type of variables. Yes, geometric variable, kinematic variables, and fluid properties. Geometric, kinematic, and fluid properties. Okay. So now, what is meant by kinematic similarity? Similar, whatever the components of the kinematics like velocity, acceleration, discharge. These are the kinematic quantities. And you take any point. You take at any point in the case of while the flow is happening. You take at any point the velocity or acceleration or flow rate in the model to the prototype. At all points, its ratio should be same. Streamlines should be similar. What is the meaning of a streamline, sir? The streamline means you know that the direction of the flow. So whatever, these are nothing but the streamlines. Let's say in prototype. This is going to be in model. So whatever, these are nothing but the streamlines. Streamline means the line that drawn along the direction of flow. Now, you take at any point, every point you take, let's take 1, 2, 3, here also 1, 2, 3. So at all points, the ratio of the velocity, see at 1, whatever the ratio of velocity is nothing but velocity ratio means velocity of model at 1 to the velocity of model at 2, velocity of prototype at 1. And at point 2, velocity of model at 2, by velocity of our prototype at 2. Both are going to be same. So at all these points 1, 2, 3, the ratio should be same. Then you are going to say it as a kinematic similarity. Kinematic ratio of kinematic quantities like velocity, acceleration, discharge should remain same at all points. So every point you take, at any point you take, the ratios of these things should remain constant. So then we are going to call it as a kinematic similarity. So in other words, you see, whatever the velocity of the model to the prototype at a point 1 is equals to velocity of model to the prototype at a point 2 is equals to velocity of model to the prototype at a point 3 and so on. They are going to be similar to each other. So everywhere the velocity ratios are going to be same. Likewise, the dimensions ratio same. Here the velocity ratios are going to be same. Then we are going to say it as a kinematical similarity. Give me a minute, please. So now let's see the next one and last one. See, this is geometry. Okay, now kinematics also okay, means the time quantities. Now there comes the last one, third one, dynamic similarity. Dynamic similarity. Okay. So now, in the case of the dynamic similarity, what is the meaning of dynamic similarity, sir? Similar here. So similar in forces. So similar streamlines should be similar, then kinematic similarity. Shapes should be similar, geometric similarity, and the forces are should be in means similarity in the forces. Forces should be similar, then it is going to be dynamic similarity. What is the meaning of this one, sir? Ratio of corresponding forces in model and a prototype at all points are same. So what is the meaning of this one, sir? Now, can we go back a little bit and let's discuss about the type of forces that we have been discussed in our open channel flow also. Yes. Now, have you remember this? The forces acting on the liquid medium. What are the forces acting on the liquid medium? 6 type of forces. So, whatever the corresponding forces acting on the liquid medium and their ratios at any point, their ratios are going to be same. That's nothing but the dynamic similarity. That is known as dynamic similarity. Now, there are different ratios. Inertia ratio means gravity force, viscous force, pressure force, surface tension, and compressible force. Now let's go back. Let me see those forces again. Now, if I say Fi as inertia force, Fg gravity force, F mu viscous force, Ft surface tension force, Fp pressure force, Fp pressure force, and at the end Fe compressible force. So you know there are 6 different type of the flows. Now, when do you say the dynamic similarity is a similarity? Similarity means the ratio is same. So now, whatever the ratio of the inertia force in the model to the prototype, the ratio means model to prototype. Force ratio means inertia force ratio is equals to gravity force in the model to gravity force in the prototype, viscous force in the model to viscous force in the prototype, and so on. All the force ratios must be same. Then they are going to be completely similar to each other. All the force ratios must be same. Then they are going to be completely similar to each other. So keep that in your mind, my dear. All the forces are going to be same. So now this is inertia force ratio, gravity force ratio, viscous force ratio, whatever the force ratio, at every point that force ratio should remain same. Now let me discuss about these two itself. Let me discuss about these two, and let me take this model to the one side. Then inertia force to gravity force of model to inertia force to gravity force of prototype. Yes, sir. What is the ratio of inertia force to gravity force? The ratio of the inertia force to gravity force, root is nothing but the Froude number, and roots gets cancelled on both sides. Then from here onwards, can I say that ratio of Froude number in the model is equals to Froude number in the prototype, where Fr is known as Froude's number, where Fr is known as Froude's number. Whenever the corresponding dimensionless number is similar in both the model and the prototype, means in model whatever the Froude number, for example, if the Froude number is going to be 1 in the model, means 1.5 in the model, in prototype also it should be 1.5, then they are going to be said to be dynamically similar to each other. Then they are going to be said to be dynamically similar to each other. Similarly, now if the forces are going to be dominant forces or viscous forces, then from here onwards we can say Fi to the F mu of model to Fi to the F mu of prototype. You see, you just crisscross it. You just crisscross it. By using these two, I get this. And by using this, I'm going to get this one. Okay. Now, from here, I can say the Reynolds number of the model is equals to Reynolds number of the prototype. So, where Re is known as a Reynolds number. So, at the end, what I want to say here is, in a given fluid system, whatever the prime non-dimensional number is there, and if that number in the model and the prototype are similar, then it is said to be dynamical similarity. And keep that in your mind. For the dynamic similarity to be happen, It's not all assumptions. For the dynamic similarity to be happen, the pre-required conditions are geometric similarity and kinematic similarity. So, if a model and prototype are said to be dynamically similar, they are completely similar to each other. So, I can write the note points as sir, actually you said the velocity depends upon shape size, but when we reduce the shape of prototype, then in model velocity changes, Froude number changes, no, sir. That's what, sir. See, the ratio of that forces should remain same. The ratio of the velocity should remain same. When the ratio of the velocities are same, then the corresponding Froude number ratio is also going to be same. Whatever the velocity magnitudes, I don't care, but at every point I take, at every point, its a ratio should be seen. The magnitude of the velocity in the model, it is maybe 1 meter per second velocity. In prototype, it may be 10 meter per second. Understood? So the magnitudes are not same, but the ratio of those magnitudes are there, right? That should be same. Okay. Now, come to the note point. The note point is for dynamic similarity, the pre-required conditions are geometric and kinematic similarity. Geometric and kinematic similarity. So, which means if I say the model and prototype are dynamically similar to each other, then they are going to be completely similar to each other, because for the dynamic similar to happen, for the Froude number to be same, means the Froude number, for the Froude number ratio to be same, then obviously the velocity ratio should be same. The velocity ratio should be same. Okay. So now, if model and a prototype are completely, if model and prototype are completely dynamically similar, then they are completely similar to each other. They are completely similar to each other. So now that's the point. So in the question also, if I do mention the given model and prototype are dynamically similar, which means then they are going to be completely similar, because if I say they are dynamically similar, obviously the pre-required conditions are geometric and kinematic similarity. If there is no dynamical similarity, then there is no kinematic and geometric similarity also. Okay. Now let's see the laws of similarity. Let's see the laws of similarity. Okay. So finally, what I want to know is if the Froude number is going to be similar in the model and prototype, then open channel flow models are completely similar to each other. And if Reynolds numbers are going to be similar, then the corresponding models and prototypes are completely similar to each other. So now let's see the laws of similarity. No. Laws of similarity. What is the meaning of loss of similarity in that number 1? Freud's law of similarity. What is the meaning of Freud's law of similarity, sir? Whenever the Freud number in the model to the prototype are going to be similar to each other, whenever the model means whenever the Freud number in the model to the prototype are going to be similar to each other, they are dynamically similar to each other. Yes or no? Because when both are same, then they are dynamically similar to each other. And if I say model and the prototype are dynamically similar, then they are completely similar to each other. So what I do is, I take this channel. So for the given flow, what are the flow I am going to send up? I am going to find out the Freud number here. And in the case of the model, I am going to find out the Freud number. So if the both Freud numbers are same, if prototype and model Freud number are same, then they are completely similar to each other. In last words, whatever the Freud number in the model and the prototype are same. Because the Freud number is not depends upon only velocity, my dear. What's the Freud number? Tell me. Fr is equals to V by root GD. So in model and prototype, the velocity magnitudes are different. In model and prototype, the depths of magnitudes are different, but the ratio of those velocities and the depths should be same. That's the meaning. Okay. So now you see that. So when the Freud number in the model means, what is the Freud number? V by root GL. In the case of model, V by root GL. In the case of the prototype. Okay. In other words, Vm by root of Gm Lm is equals to Vp by root of Gp Lp. Now let's write down the ratios now. What is meant by ratio? The ratio means, see, ratio means model to prototype. Keep that in your mind. Scale ratio, dimensions in the model to the prototype. Velocity ratio, velocity of the model to the prototype. Depth, force ratio, forces in the model to the prototype. Okay. Now I can write this as Vm by Vp is equals to root of Gm by Gp into root of Lm by Lp. Root of Gm by Gp into root of Lm by Lp. What is Vm by Vp, my dear? What is the meaning of Vm by Vp? The meaning of Vm by Vp is nothing but a velocity ratio. Can I write as a velocity ratio? So now, finally I can write the velocity ratio is equals to, whatever the velocity ratio is nothing but root of Gr into root of Lr. So for that now, if it is a undistorted model, you know that LV is equals to LH is equals to LR. Okay. Now, which means velocity ratio is nothing but root GR into root LR. Root GR into root LR. Okay. So, root of Lm by Lp. See, this is nothing but a scale ratio, right? And which ratio, whether it's a horizontal or vertical, in the case of the undistorted model, I will type it as a root LR. But if it is going to be distorted model, you know that LV is not is equals to LH. So in open channels, the characteristic length L is nothing but D. D is nothing but a depth, right? Which is a hydraulic depth. which is a hydraulic depth. So now you tell me, does this hydraulic depth is a vertical ratio or horizontal ratio? Vertical ratio. So now there the velocity ratio is nothing but root of GR into root of LV. See now here I am taking as LV, here I am taking as LR, because in the case of the undistorted model, everywhere the scale ratio is same. So whatever this LV can be written as LR, but in the case of open channels, whatever this L is nothing but D, right? What is meant by D? Hydraulic depth. So now, which means the depth of model to the depth of prototype, the depth of model to the depth of prototype. Okay. So when the depth of model to the depth of prototype, is it a vertical ratio or horizontal ratio? That's a vertical ratio. That's the reason why I keep it as a root of L into V. Okay. Now, for the undistorted models only, I am discussing about undistorted models only. In the case of the undistorted models, the ratio from here, we can write this ratio, right? If the place of model and prototype are same, if the place of model and prototype are same, then whatever the gravity in the model to the prototype both are same, then root GR, then the GR is equals to 1. If that is the case, then what is the velocity ratio? Finally, the velocity ratio is nothing but root LR. So once I know this, telling you, repeating again, once we know this, so then if the velocity ratio, some of the people are asking, sir, how the Froude number is going to be same, sir, in model and prototype? If the velocity ratio is equals to the root of the scale ratio, then you are going to say the Froude numbers are same. So you have to keep that. Whatever the velocity magnitudes, I don't care. But the ratio of those velocity in model to the prototype should be equals to square root of the dimensions ratio. So in the case of the distorted model, this will be vertical scale ratio. Whereas in the case of the undistorted model, that vertical scale or horizontal scale, every scale is same, right? So I can write as root LR. Okay. Now, see here, this is root LR. So now if the place of the model and prototype are same, see generally our civil engineering problems deals with whom? Only earth only. But if you go for aeronautical engineering or space shuttles, so whatever the space, the rockets and satellites, everything, whatever the experiments we do is on earth, but they are going to be present in the space. So there the gravity is different, here the gravity is different. So then you have to consider the gravity also. Now, this is the condition and applications of the Froude number. Where do you see these applications? Applications is wherever the flow, open channel flow, open channel flow, over mere barrage or dam, flow between piers and so everything this comes as a flow between piers and sewers. Everywhere you see where the Froude number is going to be, used, wherever the flow is going to be open channel, then it is going to be the Froude's number. So for all the open channel flows, I am going to use the Froude's law of similarity. You have to remember this, because in examination they won't give you, they won't give you use Froude's law of similarity or Reynolds law of similarity. You have to pick out. For example, if I say a reservoir is open to atmosphere, open channel flow. A flow is passing between the piers, open channel flow. A flow is passing over the VN, open channel flow. So then Froude number comes into the existence. Now, if the velocity ratio is going to be root LR, now what may be the other ratios? Based upon this, the other ratios that we are going to see now, let's observe. Based upon this. Remember that y2 consider different gravity means it's very less. That very small change in the gravity. So generally we take it as that's the reason why place of model and prototype are same. Where you are doing so wherever we are going to construct. For example, if I want to construct the dam in America, are you going to conduct the experiment in the India? No, right? You're going to conduct the experiment in the there itself. Yes or no? Now let's see. So based upon this, the applications are number one. Now coming to the area ratio. Area ratio. What is area? What is area? M square. Horizontal dimension into vertical dimension. Yes or no? So what is area? M square. So that is going to be, for example, in the case of the rectangle, by, you see B into Y for rectangle. Now when I say ratio, then there are going to be the width ratio and depth ratio. Width ratio and depth ratio is nothing but you can observe whatever here. As I am discussing about the distorted models or undistorted models. Undistorted models means all the scales, whether it's a vertical scale or horizontal scale, both are same. So if I say area ratio, then AR is equals to LR square. Means horizontal ratio into vertical ratio. Vertical ratio into horizontal ratio. As you know, we are discussing about the undistorted models. I can write this one as a LR square. I can write this one as LR square. Similarly, volume ratio, VR is nothing but LR cube. Volume ratio. See, these are the geometric details. Volume ratio, LR cube. So now geometry just LR, but still I did not use the components. What is here? Velocity ratio is nothing but root LR. Now there comes the third is going to be time ratio. Time ratio. So now what is the time, sir? See, I know one thing. I know its velocity. Yes. What is the velocity ratio? Root LR. So now what I have to do is, what I know is velocity ratio. I want to write every other parameter. For example, you see, in the practical situation means in prototype, it required 3 hours to empty the reservoir. So now the analysis comes into the existence. So there is a reservoir and you want to empty the reservoir. So for suppose if the reservoir is going to be emptied by 3 hours in the prototype, then what should be the time required to empty in the model? In the model, what is the time required? So I need to find out the time ratio. But what I know is velocity only. So you know that velocity is nothing but distance by time. Yes. And can I write that time is nothing but distance by velocity. The time is nothing but distance by velocity. And whenever the ratio means the time of model to the time of a prototype, so it's going to be distance ratio, scale ratio to the velocity ratio. Scale ratio to the velocity ratio. See, what I am writing is, I know the velocity, so I am writing the time in terms of velocity. Then LR by, now you apply, what is the velocity ratio? Root LR. What is velocity ratio? Root LR. Now you tell me, what is a time ratio? Time ratio is also known as the square root of the scale ratio. See what I am applying here. Why I am applying VR is equals to root LR? Because I am taking the Froude's law of similarity. So in the case of the Froude's law of the similarity, the time ratio is equals to root LR. Okay. Now I hope you understood. If you have understood this, that's the remaining. There is a time ratio. Now, fourth one. Coming to the acceleration means I am discussing about kinetic variables, kinematic variables, whatever the flow problems we see, acceleration ratio. Now, what is acceleration? Acceleration is equals to velocity by time. Acceleration is nothing but velocity by time. Yes. Now, acceleration ratio is velocity ratio by time ratio. Now, what is the velocity ratio? Root LR. What is the time ratio? Root LR. Then in the case of the acceleration ratio, it is going to be 1. I am taking capital A as area ratio, so acceleration ratio is going to be small a. Now, what I am saying is, in the case of the Froude's law of similarity, the acceleration ratio is going to be 1, which means the acceleration of the flow in the model and the prototype is going to be same. For example, in a rectangular channel model, if the acceleration of the flow is 1 meter per second square, then what is the acceleration in the actual prototype? In model, 1 meter per second square, and what is the acceleration in the prototype? Same, because the acceleration ratio is going to be same. Acceleration ratio is going to be 1. Now, give me 1 minute, I will bring some water. Please report me well. Okay. Now, let's see the other terms. time, velocity, acceleration, and what are the other kinematic terms we discussed? What are the other kinematic terms? Flow rate. No. Discharge ratio. Q suffix R. So discharge ratio Q suffix R. Now what is discharge? Again I know only velocity. See what I am doing is everything I am writing in terms of velocity. Discharge is nothing but area into velocity. Discharge ratio is area ratio into velocity ratio. What is area ratio? LR square. What is velocity ratio? Root LR. Then what is the discharge ratio please? LR square into root LR. So root LR means 1 by 2, 2 plus 1 by 2. LR whole to the power of 5 by 2. I hope you understood this. See, you tell me, do you need to remember these formulas? Tell me. Do you need to remember? No. See, what I am asking you is, you just remember the velocity ratio. Once you remember the velocity ratio, whatever the other ratio they are asking, for example, if the discharge passing over a spillway, see, if the discharge passing over a spillway in the laboratory is a 2 meter square per second, 2 meter cube per second, what would be the discharge passing over a spillway prototype? What will be the discharge passing over a spillway prototype? Prototype means actual structure. Then QR is equals to LR whole to the power of 5 by 2, where LR, they will be giving the scale ratio. So don't worry about that. Now, you see, don't you think that, do you need to remember the formulas here? No. You know the velocity, you try to write everything in terms of the velocity. Now, mass ratio. MR, mass ratio. So what is a mass ratio, sir? Mass means density into volume. Mass means density into volume. Okay. So mass ratio means density ratio into volume ratio. Volume ratio. This is volume ratio. So if fluids are same in model and prototype. See, generally in open channel flow, do we deal with kerosene or any other thing? We deal with only water, right? If I say open channel flow, means if I say especially Froude number, for the Froude number, whether it is a model or prototype, we use only water. We don't use air. But for pipes, now we can use air also. So for that, I can write the density ratio is equals to 1. So the mass ratio is nothing but a volume ratio, which is going to be LR cube. Sir, why you have taken this one, sir? Now let's see. I have taken. Force ratio represented with F. Okay. So what is the force? Force means mass into acceleration. Force means mass into acceleration. FR, MR, AR. And now, what is the force ratio, sir? FR is equals to mass ratio LR cube and acceleration as a 1. So finally, what is the force ratio here? Force ratio is going to be LR cube. See, I say you either remember this or you know that force is nothing but rho L square V square. You know that force is nothing but rho L square V square. That's nothing but inertia force. I bet you better remember this one. Because why I need to remember this one, sir? Because what is there? Velocity. See, if you want to go for mass into acceleration, you need to remember the mass ratio and you need to remember the acceleration ratio. In the case of the Froude number, the acceleration ratio is equals to 1. So it will be easy for us to remember. But in Reynolds number, it is not going to be same. My dear, in Reynolds number it is not going to be same. Keep that in your mind. So now you see here again force ratio rho r L r L r. And you know that if the fluids are same 1, then what is the force ratio? L r square into root of L r whole square. Then force ratio in the case of the Froude's number, this is going to be the FR LR cube. Don't think, see whatever this is the Froude number. This is Froude number. This is a Froude number, and whatever this is nothing but force ratio. This is a force ratio. I think it's better if I write this one as FR, capital FR. Capital FR. Because may get it out. So that's about the force ratio. Now, once you know the force ratio, you can find out the pressure intensity scale ratio also. So you know the pressure scale. This is the H. Pressure ratio. What is mean by pressure? Pressure is nothing but force by area. Pressure ratio, force ratio by area ratio. Force ratio, LR cube by area, sorry, area ratio, LR square. So then what is the pressure ratio? The pressure ratio is going to be LR. I hope you can find out all these things. Yes or no? See, once you know the force, then you can find out now. Energy ratio. Can't you find out an energy ratio here? Yes. So what is energy ratio? Energy ratio means force into distance. Means whatever the work, energy is nothing but force into distance. Yes. So energy ratio means force ratio. Energy ratio means force ratio into distance, LR. So what is energy ratio? Root LR into LR. So LR whole to the power of 3 by 2. LR whole to the power of 3 by 2. Sorry. This is force, right? Force means LR cube. So now LR whole to the power of 4. So I don't need to say the remaining things because you know how to go with this. So what I want you to understand over here is how to find out the different ratios by using the velocity. If you know the velocity, see the things that you need to remember most here is force ratio and velocity ratio. If you remember these two, then you can find out everything. Because if you know force, you can find out pressure, you can find out energy, you can find out power loss, everything, because it depends upon the force only. Yes or no? And you can find out the momentum also. You can find out the momentum. What is meant by momentum? What is meant by momentum? Force into time. The momentum is force into time. Energy is force into distance. Pressure is a force per unit area. So once you know the force, you can find out all those things. And for finding the force, I'm telling you, you remember the VR, velocity ratio. So ultimately, the one point that you need to remember here is in the case of the Froude's law of similarity, you have to use VR is equals to root LR. Okay. Now, so that's all. And apart from this, I'll give you one more extra, Manning's ratio. Manning's ratio. So now, what is this Manning's ratio, sir? The Manning's ratio is going to be like, you know that V is equals to 1 by n into r to the power of 2 third into s naught s to the power of 1 by 2, right? So this slope has no units, which means can I write n is directly proportional to r to the power of 2 third by n to the power of 2 third. Yes or no? Means v, that's it. So now can I write here the Manning's ratio is nothing but what is r? What is our hydraulic radius? That's nothing but a scale, right? Lr to the power of 2 third by what is the velocity? Root Lr. So now what is the Manning's ratio? Please tell me. So 2 by 3 minus 1 by 2, then Lr to the power of 1 by 6. So this is the Manning's ratio. No matter whatever they give, you can find out the Manning's ratio here also. Okay. So I hope you understood this. Now let me give some examples based upon that. Then you can understand much more better. I hope there is no PDF they have provided for me too. Let me check that. Okay, I think they forgot to send the damage analysis PDF, but no worries. Anyways, I have things with me, so don't worry. I have material. Now let me check in the material. Now let's take the material, and in the material I am going to say that. See. So these are the classroom practice questions only. What I am going to discuss for you. There were a lot of questions were there, but I am discussing these questions. So you see, question: a model of reservoir is emptied in 10 minutes. A model of the reservoir is emptied in only 10 minutes. So the model of the reservoir emptied in 10 minutes. If the model scale is 1:25, the time required the time taken by the prototype to empty itself. The time taken by the prototype to empty itself. So what is the time taken by the prototype to empty itself? Now, you tell me please. So a model of reservoir is empty in 10 minutes. First of all, you see, when I discuss about the model studies, you observe this is a reservoir. As it is a reservoir, so as it is a reservoir which is open to atmosphere. Now, which law of similarity? Froude's law of similarity. So Froude's law of similarity I can use. And in the question I clearly mentioned what is the model scale? The scale means the scale ratio. The scale means the scale ratio. LR I have given as a 1/25, which means one part of the model is equals to 25 parts of the prototype. One part in the model is equals to 25 parts of the prototype. So now, according to that, then what is the time ratio, please? The time ratio is nothing but root LR. Now, whatever I want is time of a model to the time of prototype is equals to LR. Root of 1/25 is equals to 1/5. But given is the time a model is going to be take how much time? A model of reservoir is emptied in how minutes? T in M is 10 minutes. Now, what is the time in the prototype is 1 by 5, 5 into 10, which is going to be 50 minutes. The answer is going to be 50 minutes, my dear. So now, just now, you see, I have conducted the test in the laboratory and I got to know how much time. And similarly, simply I can replicate this. Okay, fine. You know the timing model. I can find the timing prototype. What is the scale ratio? Froude's law. Means what is the law? Froude's law. According to Froude's law, time ratio is equals to root LR. And what is the time required for the prototype is 50 minutes. How you got V in denominator? What is that V? Here this one, right? You set this N. You set this N to the other side, then V. Now there is a one type of question. I'll give you the other way also. Just give it. Now. See this question also. In the model of highway, constructed to a scale of 1:25. Constructed to a scale of 1:25. The force of water on pier was measured as 5 newtons. The force of water on pier was measured as 5 newtons. So in the model of the highway constructed to a scale of 1:25. So I am going to construct a highway on the model, means it's going to be 1:25. The force of water on the pier means you are going to construct the highway bridge on a pier, and on that pier the water pressure means the force is 5 newtons. Now the force on the prototype pier is pier. So now again, flow between piers. So what is this? Froude's law. Whenever I say the Froude's law, then you know that the force ratio is equals to LR cube. Just now we discussed. If you forget about that, also fine. Sir, if I forget that, sir, then what is it? Rho R into LR into VR square. And you know that VR is equals to LR, root LR. So force ratio is equals to LR cube. Now, whatever the force I am giving you, the force of water on the pier was 5 newtons. Whatever the model, this is model, right? Now, what is the force on the prototype pier? Force on the model is 5. And what is the scale ratio? Again, 1:25. The scale ratio is going to be again 1:25. Now, 5 by force on the prototype is equals to 1/25 whole cube. So what is the force? This is newtons, right? This is in terms of newtons. So now you convert in terms of the kilonewtons. Whatever the answer that comes up, you please convert in terms of kilonewtons and let me know. Please convert it in terms of kilonewtons. So if you convert, then it's going to be 78.125 kilonewtons. This is in terms of 5 newtons, right? So I hope you understood this. So here I have represented force ratios, right? So what is this LRQ? Okay. Now, in the same question, okay, in the same question, whatever this question, I am asking you this model also, extension. In previous question, if discharge passing through prototype is 1024 meter cube per second, then discharge passing in model is dash. So now this time I am asking you the discharge, my dear. Now this time I am asking you the discharge. So when I ask you the discharge, now for the same question, what is the scale ratio I have already mentioned? 1:25. And this time I am asking the discharge. I don't know the discharge. Don't remember this. I don't know the discharge, but I don't know. I know Q is equals to A into V. QR is equals to AR into VR. Then QR is equals to LR square into root LR. So LR whole to the power of 5 by 2. LR whole to the power of 5 by 2. Now let's see. What I have given is now whatever the discharge in the prototype is 1024 meter cube per second. I am asking you what is happening in the model. So QM by 1024 is equals to what is LR? 1 by 25 whole to the power of 5 by 2. So now what is QM, please? 1 by 25. Root of 1 by 25 means 1 by 5. 1 by 5 whole to the power of 5. 1 by 5 whole to the power of 5. And it's going to be multiplied with 1024. The answer comes as 1 meter cube per second. Sorry. What is the answer? Please tell me. 1 by 5. Whole to the power of 5 into 1024. That's going to be 0.327. I think so. That's 0.327. So round it to 2 decimals. 0.33 meter cube per second. So now I hope you can understand. See how much discharge is passing actually in the prototype 1024. Then how much it should pass through the model 0.33 meter cube per second. So here I discussed about the time ratio and force ratio and discharge ratio. I can ask you the velocity ratio also. So I can ask you what is the velocity ratio. Velocity ratio is nothing but time ratio, Time ratio and velocity ratio both are same. Now I'll give you one more question, but this time this is going to be this time undistorted model based upon the undistorted model. Question number 3. Now a river model is constructed to a horizontal scale. A river model is constructed to a horizontal scale of 1:1000 and vertical scale of 1:100 and vertical scale of 1:100. If modal discharge were 0.1 meter cube per second, then discharge in river So now I am asking you the discharge in the prototype. Yes. Now let's see. Okay. So solution, river is going to be a Froude's law of similarity only, right? Froude's law. But is it a distorted model or undistorted model? So first of all, whatever the horizontal scale ratio 1 in 1000, vertical scale ratio 1 in 100. Whenever the horizontal will not be same as vertical, then it is going to be distorted model. So in the case of the distorted model, we have to do the analysis separately. So you know that in the case of the distorted model, I have clearly mentioned you. In the case of the distorted model, I clearly mentioned you whatever the velocity ratio is root of LV. It's not LR, it's vertical. It's not LR, it's going to be vertical. What I am asking you is a discharge. So discharge is nothing but area into velocity. Discharge ratio is nothing but area ratio into velocity ratio. What is area ratio? LV into LH. In the case of the undistorted, LV is not is equals to LH. So into what is velocity ratio? Root of LV. LV to the power of 3 by 2 into LH. What is LV? So now Q in the model. What is the model here? Given whatever the discharge in model is 0.1. So 0.1 by prototype as QP is equals to 1 in 100 whole to the power of 3 by 2 by 1 in 1000. 1 in 100 whole to the power of 3 by 2. 1 by 100 square root 1 by 10. 1 by 10 cube 10 cube. So this is 10 cube and this is 10 cube, and finally whatever the discharge in prototype is going to be 10 to the power of 6 into 0.1, which is going to be 10 to the power of 5 meter cube per second. I hope you understood here. What I am doing is here, I am not taking LR. See, if it is going to be a distorted model, undistorted model, then LV and LH both are LR. LR into LR, LR square. And root LV is nothing but LR. So there that is different. LR square into root LR. Then it is going to be, you see, LR square into root LR. Then it's going to be LR whole to the power of 5 by 2. But here I am clearly mentioning you, this is the undistorted model. So area ratio LV into LH, velocity ratio, that characteristic length should be a depth. I hope you got the difference between the distorted model and undistorted model now. Okay. Why LR is equals to LV in distorted model? After all saying this also you are saying, you are asking the same question there. What to say? You see, in the characteristic length, L is equals to D. D is nothing but depth, right? D is nothing but depth. So dm by dt is equals to ym by yp. That is nothing but the LV. Okay. So that's it. That's the reason why. So these are some of the questions regarding to here. I'll give you one more question and then I'll give you the break. So this question is a very good question. Okay, so I'm not going to solve this, but I'll give you. A spillway model is reduced to scale of 1:9 and the discharge in prototype. So discharge in the prototype is some 1200 meter cube per second. The hydraulic jump of model dissipates energy of 3.5 Newton meter, 3.5 Newton meter, and the power loss of 0.25 kilowatt. 0.25 kilowatt. So now find one model discharge, two energy loss in prototype jump, three power lost in prototype jump. So this is the question. You please try to solve this. So you can find out the power also. You know that power is nothing but force into velocity. Power is nothing but force into velocity or work done by time. If you know the energy, what is power? Energy means force into distance, and power means energy or work done per unit time. Force into distance by time, force into velocity. Force into velocity is nothing but power. Force into distance is going to be the energy, and you know the discharge, area into velocity. And this is a spillway model, which is going to be a Froude's law. Let's try to solve, and you can find out the answers. Now, let's have a break and we'll start our session. See, the most important law is the Froude's law, the most important law, especially for the open Java flow purpose, then it's going to be a Froude law. Most of the questions in the previous gate also appeared in Froude's law. And then after the break, we'll be discussing about the Reynolds law and corresponding questions for that. Okay. So we'll be see that Reynolds law after the break. Have a break. Come by 9:10. 15 minutes, right? 9:05. Now,
Okay.
let's get back. The answers for this are, for the modal discharge, it's going to be 4.94 meter cube per second, and energy loss. So the energy loss is going to be 22,965, sorry, 963.5 Newton meter. This is energy loss, and power loss is 546.75 kilowatt. If you have got this one, then fine. Else, you know how to find out those energy loss. And power means C. Power means force into velocity. LR cube into root LR, power ratio. So LR cube into root LR, 3 plus 1 by 2, 3 to 6. Yes, 7 by 2. 3 plus 1 by 2. Yes. So it's going to be 7 by 2 if you substitute, and energy loss is going to be FR into LR. Energy loss is going to be FR, means a force into distance, FR into LR, that is going to be LR power 4. Okay. Now let's see. Next, come to the Reynolds law of similarity. And what is this Reynolds law of similarity, sir? So the Reynolds law of similarity is here, the Reynolds number in the model is equals to the Reynolds number in the prototype. The Reynolds number in the model is equals to Reynolds number in the prototype. And what is Reynolds number? So rho VL by mu. Rho VL by mu of model is equals to rho VL by mu of prototype. Or we can write, you know, this is nothing, mu is nothing but mu by rho. Nu is nothing but mu by rho, which is going to be a kinematic viscosity. Yes or no? Kinematic viscosity. You see here VL by mu of model to VL by mu of prototype. So now Vm by Vp is equals to, now you see here Lp by Lm, the nu m by nu p. So now this is how I have arranged, and if I would have arranged this, then what is the final answer? Vm by Vp, velocity ratio, is nothing but nu m by Vp, kinematic viscosity ratio by scale ratio. Nu r by Lr. Don't take nu r as 1. Don't take nu r as 1, okay? Because in the case of the Reynolds number, where the applications? What are the applications of the Reynolds number? Applications like fully submerged bodies. Example, submarine. Submarine is completely below water, right? So submarine is completely below the water. In the case of the submarine, so the entire water is going to be acting over surface, which causes viscous forces. When do you use the Reynolds number? When the viscous forces are dominant, then we use the Reynolds number. When do we go for the Froude's number? When the gravity force is dominant. So submarines, airplanes is completely submerged under air. When the plane is going on, it is completely submerged under air. And fully are closed flows like pipe flow. Now, flow over plates, windmills, aerodynamic forces, whatever the trains and us. So mostly the viscous force is going to be takes place. So flow over plates, flow through pipes, and fully submerged bodies. Wherever you see the viscous force, there you are going to use the Reynolds law of similarity. And in the case of the Reynolds law of similarity, now I hope you understood. Does VR is going to be same in both the cases? Does VR is same in both the cases? No. The VR is not going to be same in the both the cases, sir. Okay, so now what is airplane? Airplane, right? What is airplane? Plate means what? Flow over plates, my dear. Flow over the surfaces. Whatever the flow over the surfaces means in the fluid mechanics, you came across this flow over plates, drag force. I hope you remember the drag force on bodies. For example, if I throw a ball, and when the ball is passing, this ball pierces the air, and this air will offer some resistance, right? That is known as a drag force, and it is acting over the surface, which is nothing but viscous force. So here, wherever you see this, there we are going to apply the Reynolds law of similarity, and once we know the we are, you know, area ratio is known as LR square. Volume ratio is known as LR cube. Now, next, time ratio, velocity ratio, or LR by velocity ratio. So, LR by what is velocity ratio? Nu R, and LR, hold the numerator, LR square by nu R. So, I don't remember. In the case of the Proud's law, time ratio is very simple, root LR. Here I cannot take nu R as constant. Are you going to take the kinematic viscosity as constant? No. Because when I discuss about the Reynolds law, then lot of fluids, air would be there, water would be there, different fluids has different kinematic viscosity and density. Okay. Time ratio. And coming to the acceleration ratio, next. Acceleration ratio means velocity ratio by time ratio. So velocity ratio nu R by LR, and time ratio, now just now we discussed what is time ratio? LR square by nu R. Okay, sorry. Inversely, right? Yeah, 1 by, right? So 1 by means nu R by LR square. So what is acceleration ratio? Nu R square by LR cube. Are you going to remember this? What my suggestion is, please don't remember. You know the velocity ratio. Once you know the velocity ratio, you can find out the time and you can find out the acceleration also. Okay. And if I ask you the discharge ratio, area ratio into velocity ratio, LR square into nu R by LR, which means LR into nu R. And force ratio. Force ratio means rho L square V square. Rho L square V square. Rho R LR square VR square. Okay. Now, FR is equals to rho R into LR square. VR square means what is VR, please? What is VR? VR means nu R by LR. Nu R square by LR square. LR square will get cancelled. And now the force ratio is equals to rho R into nu R. What is nu R? Nu R by rho R whole square. So finally, the FR is equals to nu R square by rho R. If you want to remember, you remember only this one in this case. Because the most of the questions that I ask on the Reynolds number is the force ratio. If you don't remember also fine, you know this formula, force, and from the force rho L square V square. Always you try to remember this one only, because it will provide your velocity. And if it is a Proud's law, VR is equals to root LR, And if it is a Reynolds law, VR is equals to nu R by LR. And I don't go beyond this because once you know the force, if I ask you energy ratio means a force ratio into scale ratio. If I ask you pressure ratio, force ratio by area ratio, power loss ratio is equals to force ratio into velocity ratio, momentum force into time ratio. Okay, so you know the remaining things because once you know the force, multiply with LR, energy ratio, divided with AR, pressure ratio, power ratio, force into velocity. Okay, so I don't remember too many things here. I do remember only first one. I'm not doing any speed rate. I'm not going speed over here. I'm just saying that whatever the things we replicated, I'm just finding over here the same thing. How do we see this AR, VT by R? I don't want you to remember all these things. I want you to remember this formula and this formula. That's it. And you know how to go with the remaining things also. Okay. So this is a Reynolds law of similarity. Okay. And apart from that, you see, you go back. There are these many forces are there, right? So these many forces are there. Okay. So far and so good. I have discussed about gravity and viscosity. Gravity, if the gravity force is going to be dominant, we call it as a Froude's number. And if the viscous force is going to be dominant, we call it as a Reynolds number. Then what about surface tension, pressure, and elasticity? Now let's see those numbers also. But in our civil engineering, we don't require those things. In civil engineering, we almost use Froude's number and Reynolds number only. Now coming to the next number. For this, I am not going to do the analysis. So Euler's number represented with the ER. Euler's number is equals to, it's a ratio of inertia force to pressure force. Then whatever the inertia force to the pressure force, and the similarity means it should be same in both the model and prototype. See, you don't need to worry about the usage of this one because in our civil engineering we don't go these many things. So Euler's number, pressure force. So where do you see this one? The significance is, or application is, where pressure force are dominant. Wherever the pressure forces are dominant, we use this Euler's number. And in cavitation studies that you will get in fluid mechanics or in environmental engineering also, you may come across the cavitation due to high pressure, due to cavitation studies and water hammering. So these are the terms that you are going to see in the fluid mechanics. Cavitation studies and water hammering, but we don't use much. We do use pressure force along with the viscous forces also. So when I say viscous force, then I have to use the Reynolds number. Yes. And pressure force, then I have to use the Euler's number. Yeah, it's today is the last class. Yeah. Now coming to the fourth one, this is Euler's number. Next, Max number MR. max number mr. So mr is equals to the max number is equals to, so it's a ratio of inertia force to the max number is going to be elastic forces. Wherever you see inertia force to the elastic force, we use max numbers. So here max number in the model is equals to max number in the prototype. Now here significance is, so here significance is a high compressible flows, where high compressible flows, highly compressible flows means examples jets, rockets, etc. So in the case of the propellers, jets, rockets, there the elastic forces are compressible because when a rocket is going to be launches, it compresses the air, it compresses the surrounding air and it is going to be travel. But does water is going to be compressible? No. So water is incompressible, and this max number is used to study, just like Froude's number says that subcritical, subcritical, here subsonic and supersonic waves. Just need to know the names, that's it. And now the last one is Weber number represented with the WR. Now, what is WR, sir? The WR is going to be, it's the ratio of inertia to surface tension. It's the ratio of inertia to surface tension. So the Weber number of the model, similarity means the Weber number of model is equals to Weber number of the prototype. And the significance here is significance. So wherever the surface tension forces are dominant, surface tension forces dominant, there we are going to use the Weber's number. And example is, in the first chapter of your fluid mechanics, you are going to see the water bubble, air bubble formation. How the water bubble, see, when rain occurs, the droplets are going to be spherical in shape or not, and that shape is due to the surface tension. And when we the bubbles, air bubbles and soap bubbles would be there or not, and for those soap bubbles also you can see that spherical shape, that is due to the surface tension. So example, water and air bubbles formation. There again in fluid mechanics part 1 you are going to learn those. So these are the other numbers apart from the Froude's number and Redal's number. So we don't need to worry, we don't give much importance for those numbers. We just need to know what is what, that's it. Why always inertia force is the numerator? Because inertia force means whether the body is in motion or not, the common force acting on the fluid is inertia. So you have to say whether means the inertia is going to be the moving, and who is going to be resisting over there, or who is going to be causing the other forces are nothing but pressure, viscosity, elastic, and all those things. Okay. Now, so that's about the other numbers. This is about the Froude's law of similarity, and the last topic in this chapter, scale effect. With this, we are going to complete the dimensional analysis. So whatever the three objectives, homogeneity completed, and dimensionless groups completed, model studies also completed. So in order to study the model, you need to know that all the three are similar to, means geometric, kinematic, dynamically similar. When that is going to be happen? When the corresponding dimensionless group number is similar. Okay. So now coming to the scale effect. So any hydraulic system, may be affected by more than one force. See, a hydraulic system may gets affected by more than one force. For example, if you take the cavitation study, my dear, just now I mentioned, if you take the cavitation study, in the case of cavitation study, viscous force is there and pressure force is there. So there you have to consider both. And similarly, in the case of the ships also, you can see, means wherever you see some of the systems, there may be an effect of more than one force. There may be an effect of more than one force. But so far and so good, what I am taking is only one force at a time or not. If the gravity force is predominant, I am asking you use Prout number. If the viscous forces are predominant, Reynolds number. Arey sir, if more than one force is going to be there, then what to do, sir? What happens if I take only one force? So now, if only one force is considered by neglecting remaining, the resultant error is scale effect. The resultant error is known as a scale effect. So if you consider only one force, then the resultant error is going to be the scale effect. Okay, and to reduce scale effect, all forces should consider. Now let's take an example. The example is partially submerged ship. So if you take a partially submerged ship, it's not a fully submerged, but partially submerged ship. So this is the water. So this is the water, and this is going to be a ship. You can see this one. Whatever, this is a ship which is partially submerged. Okay. Now you see below this water, this body is going to be acting under a force. These are forces known as viscous forces. So below water surface, viscous force would be there. Okay. And above, as it is a free to atmosphere, while it is moving, while the ship is moving, the gravitational force also present here, gravity force. So whatever the portion of the body below, is under submergence, means the submerged part is under viscous force and the free part is under the gravity force. Here, viscous and gravity forces are dominant forces. So in this case, both the viscous force and the gravity forces are going to be dominant. When both viscous force and the gravity forces are going to be dominant, then I cannot take one force. If I take gravity force by neglecting viscous force, I can get some error known as scale. And if I take viscous and if I neglect gravity, then also I can get the error. Okay. So now let's see. For no square effect, I have to take both the consideration. Now, for the viscous force, for viscous force is dominant, then the Reynolds number, according to the Reynolds law of similarity, according to the Reynolds law of similarity. Reynolds law, you know that the velocity ratio is nothing but mu r by L. And according to Freud's law, according to Freud's law, nu r is equals to VR is equals to root LR. So now, for no scale effect, what I'm going to do is I'm going to equate these two. Equating both for no scale effect. If you equate both, now you see nu r by LR is equals to root LR. If you equate both, then nu r by LR is equals to root LR, because this is a velocity ratio. This is also velocity ratio. Now from here onwards, nu r is equals to LR whole to the power of 3 by 2. LR whole to the power of 3 by 2. So now finally, this is the equation. See, just simply what you need to know here is, when there is a more than one force as acting in the system, you don't neglect that force. You have to consider those forces by taking both the numbers and both the laws of similarities, and you just equate both. Then that represents a no scale effect. So with this, we have completed the dimension analysis. There's a let's see one question based upon the scale effect and one question based upon the Reynolds number, so that we have completed all the questions. See, I have given a questions for the earlier things, how to predict the dimensionless pi terms, how to find out that pi terms. For 2 to 3 examples I have given there, and for Freud's number, means for Freud's number I have given some examples. Now let's see one example for the Reynolds number and scale effect, so that it will be there with you. Okay. In a flow condition, where both forces, viscous and gravity forces, are dominant, both viscous and gravity forces are dominant, and the ratio of kinematic viscosity of model to prototype is 0.0894. Now, under dynamically similar conditions, scale ratio is scale ratio. So now, just now I mentioned that when the viscous and gravity forces both are predominant, now you know both viscous and gravity are dominant. When both are going to be dominant, my dear, then what you need to look over here is what I would like to do here, nu is equals to LR whole to the power of 3 by 2. I want LR, so nu 0.0894 whole to the power of 2 by 3. What is this value, please? The value over here. So what's the value, please tell me? 0.0894 whole to the power of 2 by 3. So 0.1999. So 0.1999. And if you take in terms of ratio, so then the ratio is going to be 1:5, 1 by 5, 0.2, right? It's going to be 1 by. So I hope you understood this question. Now let's see one more question regarding to the no question. Yes, see. So this is based upon the Reynolds number. This is the last question that I am discussing. The remaining things you can go through, but you just need to know. See, in the dimension analysis, they cannot ask too much into the depth. They can ask you the basic things only. Okay. So now, air flows over a spherical storage vessel of diameter 4 meters at a speed of 1 meter per second. Air flows over a spherical vessel of diameter 4 meters at a speed of 1 meter per second. Okay. So apart from this, to find the drag force, to find the drag force, to find the drag force on vessel, a test run was carried out in water using a sphere of, see now you see there is some spherical storage vessel, on the top of it. So on the spherical storage vessel, on the top of it there is air, and that air is moving at a speed of 1 meter per second. Now, in order to find out what is the drag force acting on that vessel due to that air, we are going to conduct the test in the water. See now, whatever the fluid in the reality is air, but whatever the fluid I am taking is water. So this is a prototype and this is a model using a sphere of how many mm? 100 mm, just 100 mm, just 100 mm. And dynamic viscosity of water. So the dynamic viscosity, the density and dynamic viscosity of air, dynamic viscosity of air is given as 1.2 kg per meter cube, 1.8 into 10 to the power of -5 Pascal second. Similarly, density of water, dynamic viscosity of water is also given as, so what is density of water? You know that 1000 kg per meter cube, and dynamic viscosity of water 10 to the power of minus 3 Pascal second. The drag force on the model, if drag force on model is 4 newtons under similar conditions, the drag force on prototype is dash. Under similar conditions, the drag force on the pipe is going to means prototype is going to be dash. See, they have given these much question. The point number one, what I am going to suggest you is, once you know this one, first of all, what is this drag force? Drag force is nothing but Reynolds law of similarity. Reynolds law of similarity. Okay. So now, as it is Reynolds law of similarity, you know that in the case of the Reynolds law of similarity, first of all, you need to know who is model here. Model is nothing but here as a air. And who is a prototype? Sorry. Model is about water. Who is a prototype? Prototype is about air. Okay. Now, whatever the drag force on the model is given as 4 newtons, and what is the drag force on the prototype? Okay. So now you know that force ratio is nothing but rho r LR square into VR square. And the only thing that I asked you in Reynolds number is to remember velocity ratio and force ratio. And what is the force ratio? Force ratio means mu r square by rho r. Force ratio means mu r square by rho r. Yes or no? So force ratio is equals to mu r square by rho r. That's the one thing. So now what we do is we are going to substitute these values. So force in model to force in prototype is nothing but mu of model to mu of the prototype to square into rho of prototype to rho of model. So whatever the force in model is 4 by Fp is equals to, who is the model here? Model is water. And what is the viscosity of water? 10 to the power of minus 3 by viscosity of air. 1.8 into 10 to the power of minus 5 whole square into, now prototype is going to be air. So what is our density of air? 1.2 by 1000. So find out the Fp value. And what is the Fp value? Please tell me. So if you find out, then the answer is going to be 1.08. 1.08. So that's all with this question. See, simply what I am doing is I want force, right? I want force. That's it. I want force, then I got none. In the same question, if I would have asked, what is the velocity ratio? What is the velocity ratio? If I would have asked in the same question, what is the velocity ratio? And what is velocity ratio? Nu r by Lr. Nu r means mu r by rho r into 1 by Lr. So this velocity ratio, I am asking you the velocity ratio, my dear. Okay. So nu r means nu m by nu p into rho p by rho m into 1 by Lr. 1 by Lr means whatever the dia, they have given what is the dia in the case of the storage vessel? The dia of prototype is going to be 4 meters, whereas dia of the model is just 100 mm, right? 100 mm. 100 mm means 0.1 meter. See, I'm asking you to find out this. No, it's not drag force will increase. See, here the drag force, which drag force I want? Air. But which one I have taken? Water. So some of the students are asking, sir, for model it is 4, why prototype is going to be 1.08? It's not same fluid. Water has more viscosity than air or not. So water has 4, and if the air will be obviously less. So 1 by LR. 1 by LR means LP by LM. So now find out the velocity ratio also. 10 to the power of minus 3 by 1.8 into 10 to the power of minus 5 into 1.2 by 1000 into LP means dP by 0.1. So what is the velocity ratio? Please tell me. This velocity ratio also you please tell me. In terms of 1 in, tell me. Okay, so that's all, my dear. Hope you get this answer. You find out the answer, and for you, for the practice questions, I am going to give you. For the practice questions, I will be giving you some extra questions for you. I will be attaching that along with the PDF today. And one more thing. So today is 28th. I'll try to possible by the management within a 1 week. We'll try to conduct a test on the FM2. So as a lot of people are asking, sir, what about the test? Already we are uploading the questions in the test series, my dear. See, already I was busy in preparing the questions for the test series. If you have already taken the test series, then fine, you please go through the test series. I have already provided the questions over there. But that once let's see about the management. So how their plans are there. So already test series is going on. So that's the reason why. Earlier I have kept the test because by then the test series was not started. So but as of now the test series was started. So that's it from me for you regarding to the fluid mechanics part 2. So that's about the fluid mechanics part 2 and dimensional analysis. See, we have been discussed around 293 pages this time. 290 or 280 some pages, some odd pages this time. So these are all the open channel flow and dimensional analysis. Solve with the total from starting onwards to the ending. Okay. So I hope you understood and enjoyed the subject. I hope so. And for the people who have not completed geotech, will be taking, and it's not been scheduled yet. And I don't know what is the subject for the next schedule also. That will be let you know by the corresponding faculty, because so afternoon also. So afternoon also. Yes, any topics remaining for the EAC? Yes, for the EAC is there. I told you already. For the EAC it is there. For EAC, see, tomorrow and day after tomorrow, EAC students, you have to come. We are going to discuss about the flow measurements devices. See, the flow measurement in channels, that is very, very less, that you don't need to worry about it. Not even a single question has been appeared so far. Not even a single question. Okay, so don't worry about that. Now, you see, for the IES people, tomorrow and day after tomorrow, by Sunday, we will finish the syllabus. Morning, same timing. And for the GATE people, the next subject will be let you know either by means of mails or messages, or it will be uploaded soon. What about the next subject? So you please go through that. And for the geotech, means the people who have already completed the geotech, I hope you people are doing fine. And within a week, we are going to provide the doubt clearing sessions. And anyways, I am available to you. I have given my phone number to you and I have given my mail ID. So you can please mail to that, and if I don't give reply through the mails, because I used to get a lot of mails. So, and you can send me that question through the WhatsApp. So if that question is going to be really important, and if you have not done completely, or if you, even though you tried it and you didn't got that, so if you don't get that questions, you send me through the WhatsApp also. I can answer through that. That's all from my side. I hope you enjoyed the classes, and all the best for you for the other. Tomorrow, will you teach flow measurement device? Yes, I am the one. Yeah, see, for the gate people, you can join to the tomorrow's lecture. If there is no lecture for you, you can join. That's not an issue. It's up to you. The gate people, it's up to you. So if you want to join tomorrow's lecture, that will be much more useful for you, not for the examination, but it will be useful for you if you have a time. And if you are studying the third year, and that will be useful for your semester examinations also. Okay. I wish you teach all the subjects. No, I cannot teach anymore. And the two subjects in my pocket are Geotech and OpenChan Flow only. But yeah, now let's see the doubt clearing session. It's 10 o'clock. I'll take a doubt clearing session for the next 15 to 20 minutes. So let's have the doubt clearing session. I'm enabling the raise a hand option, please. Mr. Sachin, please speak out. Mr. Sachin, please speak out.
Sir, good morning, sir. Can you hear me, sir?
Yeah, I'm hearing you. Tell me.
Sir, one doubt, sir. It is not related to subject.
Yeah.
But, sir, for me, fluid mechanics is not completed, sir. But you have taught dimensional analysis chapter here. But
Yes.
some students commented that in fluid mechanics also dimensional analysis is taught. What is the difference between the teaching?
Nothing difference is there. Nothing difference is there, because once you complete the fluid mechanics part one, there the discussion is more towards the pipes. Okay, Froude's number.
Okay, sir.
So what we discussed about open channel flow, na?
Yes, sir.
See the basics, everything is same. Whatever the data I have given you here, na, there are the same thing will be there. Okay, but the problems there, they focus more towards the Froude's number rather than the Reynolds number. Sorry, Reynolds number rather than the Froude's number. Here, entire my focus is about whom?
Froude's number, sir.
Yeah, why we discuss open channel flow, right?
Yes,
so I have given only one question for the pipe flow. Yes or no?
Yes, sir. Yes, sir.
So if you see there the type of problems will be different. That the topic center is different. If I don't think they are going to teach the fluid mechanics in the means if the online class are going on, I don't think they will teach the dimensional analysis in fluid mechanics part one, because as I have already taken. Okay.
Okay, sir. Okay.
Yeah. Okay, Sachin.
That's it, sir. Thank you, sir.
Yeah. Mr. Gopi Golaka. Nice name. Gopi.
Good morning, sir.
Good morning, Gopi.
Sir, my doubt is regarding adverse slope condition, sir.
Yeah, tell me.
Sir, actually, every profile should meet the NDL, no, sir. It should start with NDL and ends with NDL, no, sir.
Yes, yes, yes.
Sir, but in adverse slope condition, it is meeting CDL, no, sir.
No, it's not meeting CDL.
Sir, in adverse slope condition, Yn is infinity, no, sir.
Yn is infinity. What is the meaning of Yn is infinity?
So, normal depth plane also, we don't see normal depth plane, no, sir.
That's what I'm saying. Whatever the level of water you are going to send, that will store. That's it.
Sir, my doubt is about.
And see, listen to me. You cannot take the individual adverse slope.
Yes, sir.
You cannot take the slope directly as an individual adverse slope. You have to add before and after some other slopes. You have to add either mild slope or steep slope. You cannot take a single individual slope.
Okay, sir.
If you take individual adverse slope, then there is no flow at all.
Okay, sir. So what
see, when you are going to take that, right? Yeah, I'll show you this. If you are taking adverse slope like this, you cannot allow the flow directly over here. So this adverse slope must be, okay, fine, let's say there is going to be mild slope, and then there is going to be the steep slope, and this is going to be the adverse slope. Okay, like this you have to consider. If you consider this now, what happens is, you see, In the case of the mild, there is going to be NDL. Okay. Are you able to understand?
Yes, sir. Yes, sir.
In the case of the steep, NDL is going to be less or not?
Yes, sir.
And in the case of the adverse, NDL is going to be infinity. So for what happens over here is water level rises and reaches asymptotical to horizontal infinity. Yes or no?
Yes, sir.
And then it is going to be false. CDL here would be there, and then it is going to be reaches to the NDL over here. So
Sir.
though adverse is there, listen.
Okay, okay, sir.
There,
Sorry, sir.
the adverse slope cannot be taken as an individual slope. It has to be attached to some other slopes.
Okay, sir.
Yeah.
Sir, I'm talking about A3 profile, sir.
Yeah, you are talking about A3 profile. Okay.
Yes, sir. If A3 profile is there, sir, there is a chance of hydraulic jump, no, sir?
Then there is a chance of hydraulic jump. Yeah, reverse this. Just simply reverse this.
But we didn't mention the hydraulic jump in the adverse slope condition, no, sir.
That's what now. See, adverse slope, we don't use much. Based upon the usage, we say, right? We do use mostly mild slope and steep slopes.
Okay, sir.
Yeah. Based upon the practical situations, I said there.
Okay, sir. Sir, but these are imaginary situation, no, sir?
No, based upon the topography. When the topography is going to be changes, if suddenly changes from low lying area to high lying area, there you have to change the slope or not.
Yes, sir.
There. It's not imaginary conditions. See, whatever I am showing you, the variations like this, rises and falls, something like this, right?
Okay, sir.
In reality, you don't see this much variation. In reality, you see this much variation. That's it. See,
Okay.
rises and then it's going to be falls. In reality, the variation looks like this. Understood or not?
Yes, sir.
But for better understanding, I am drawing the figures with these ways so that you can see, okay, water level is going to be rising asymptotical, reaching, and then falls and asymptotical to Indian, something like this. Okay?
Okay, sir. I understood, sir.
Yeah.
Thank you, sir. Thank you very much.
Yeah, okay, okay. Mr. Elaya, please speak out. Mr. Elaya, please.
Hello, I'm
Yeah,
Marvel, sir.
Yeah, yes.
Sir, I have a doubt in dimensional analysis, sir.
Tell me.
Sir, in that, if you take in kinematic similarity, there is a velocity and acceleration is there, no, sir. If you take acceleration, we get different answer, sir.
Where?
In the dimensional analysis, sir.
Yeah, I'm asking you in
I think I'm right, yeah.
only. What happened? Tell me.
Sir, if we take instead of velocity, if we take acceleration due to gravity, we get a different answer, sir.
For which question, my dear?
We are getting. You said only one question, sir. One question, Rashid, sir.
Regarding to
Yesterday class, sir. Yesterday class.
in yesterday's class,
Buckingham Pi theorem, sir.
this one.
Yes, sir. This one. If you
Yeah.
take instead of we get different answers.
Where is V, my dear? Here. Yeah. Why you take G? Why you take G? See, when I was taking.
Why don't I?
See, when I was taking these values, I said you can take F above or below. But while I am saying this one, I told you that V and rho, why we prefer is compared to V and G, V is going to be less complex than G or not. In that, you see the dimensions for the velocity Lt to the power of -1 or not.
Yes, sir.
And for G, Lt to the power of -2. Which power is more?
Yes, sir.
So the more the power, the more the calculations.
Yes, sir.
Now you tell me, are you going to for complexity or simplicity?
Simplicity, sir. But if we take complexity, we get answer, right, sir?
No, that's what. Nah, if every possible way is going to be discussed, then what is the correct answers there? There must be only one correct answer, right?
Okay.
Hmm.
Okay, sir. Thank you. Sir, in the problem, third problem, sir,
You
dimension analysis.
listen. If in the case of the kinematic variable, mostly velocity is the one that is repeating variable.
Okay. Okay.
And in the case of fluid property, mostly density is the one because those are the ones
Okay.
least powers.
Okay.
Okay, tell me.
Sir, in the similarity, sir, Cross number similarity. There is a problem. A river model is constructed in a horizontal scale 1
Yeah,
is to
yeah,
power
tell me, yeah, tell me.
1000.
Hmm.
Sir, in that velocity ratio root L, sir. Why vertical? Why not horizontal, sir?
I
That
discussed that
problem.
point 3 times in the class itself. Now, I mean, yeah, I hope you are seeing this. Yes.
Yes, sir.
Yeah, what is L? Characteristic length Arna.
Yes, sir.
In open channel flow, while taking Froude number, the L is taken as D Arna.
Yes, sir.
What is D hydraulic depth?
Sir?
What is D, my dear? Hydraulic depth Arna.
Yes, sir. Hydraulic depth.
Depth means
Wherever
vertical
it is.
dimension and horizontal dimension.
Okay.
The
Vertical
limit ratio
dimension.
I have
Thank
to
you.
use.
Sorry.
Yeah. Yeah.
Vertical ratio.
Yeah.
Thanks.
Okay. Okay. So that's about. There is no other people who has to ask. Hope you people got the. Thank you, Vivian. And thanks to all of the people to bear me. And especially my class timings. When the class is at 7 o'clock, I never be at 7 o'clock. I used to get late 7 p.m. means 7:05, 7:10. So I cannot take the FM1 because I don't know means I don't know that subject FM1 that much. Okay, I cannot take it as a fluid mechanics part 1. Some preparation tips for open channel flow. Open channel flow, you just write down all the formulas for the open channel flow starting onwards. So you focus more on the GVF and specific energy. GVF and hydraulic jump is much more important because recent days they are taking more towards the GVF and hydraulic jump only. And especially for ESC, it is going to be the GVF in ESC. Okay. And pile load test is there, right? Okay, laterally loaded piles, and that session would be separately given for you. So for the geotech completed students, as there is one topic added extra, laterally loaded piles, that we will be discussing. But for that, it requires a separate session. So it will take time. Don't worry. Meanwhile, you complete the other syllabus. I'll take that. Don't worry about that. I'll take definitely. Once again, thank you, everyone. So. Yeah, I'll be taking geotech. Okay, so now I hope some of the people has to attend the other class. At 10:30 hydrology class is there, and some other people has colleges. So I'm leaving the session. And anyways, so you have my details, and I already provided that in the PDF that I have provided you. So if you get any doubt regarding to the subject, and if you're feeling stressed or frustrated, and if you're feeling a little bit helpful, don't worry, you just message me. And if I'm really free, and so I'll definitely give a reply to you people. And at this point of time, not only the subject, you require something more than that. You require something for what is the reason that you need to do. Because over the period of time, due to this continuous preparation, you get frustrated. And there is a one particular point of time there you lost the patience. Though you study completely, and while you are solving the problems, you may end up with silly mistakes. But I'm telling you, that is going to be common for everyone. None of us, you, or whatever the past students who has taken coaching, and the faculties, even me also, I'm considering myself also. None has got the gate ranks without doing a mistakes. Everybody does mistakes, and everybody does, and everybody will do also. So don't worry if you are getting mistakes, and if you are getting negative marks also, don't get stressed, and don't make sure yourself lower. And your defensive mechanism should be always in a higher position. Keep that in your mind. So if you really need any sort of help, you just message me. I'll try to be as helpful as I can. So that's it for me, means from me. And I'm leaving. All the best for you. And we'll see in the upcoming days for the other people, for the geotech, we'll be seeing. Okay. Yeah, take care, and I'll also miss you people. Though I cannot see you virtually, means though I cannot see you physically, but I can feel. So the messages that I get from you, that's a way better for me. Okay, miss you all, and goodbye and good luck.